It's like the Berkeley time of the Berkeley time. Well, I do appreciate all of you here. What? Oh, the one day is? Okay. I think so. Like with wavelet? With wavelet? Yeah. Do you want to do it? Do you want to? Yeah, I didn't realize what it was. Okay, welcome. EE123, lecture 29. Just a second. Woo! It snuck in like at the last minute. Thanks, I appreciate coming here in such a rainy day. Okay, a few things. Again, frequency measurement challenge due tonight. Give it a shot. It's worth money. Project updates is meaning I met with some groups. I haven't met with all the groups. You have to meet with me by next Wednesday. I'll post tips for I'll post tips for the project of how to start. But if you're going to do the preferred project, start with the compression part. Okay, just start that. Make that module work well. Okay, because there's plenty. There's not that much time. Again, like you'll see, the end of the semester will come soon, so you can start immediately on the compression part. You must meet with either one of us after you met with me. Okay, so every week to follow up. And what we want to see is we want to see progress. Okay, we don't want to see like, oh, we didn't do nothing, we didn't do nothing. Oh, we did a project, but this thing didn't work. So it's better to see like, yeah, we did this, and we're having trouble with that part. Okay, then you get some advice, and then next time progress. That will be part of the evaluation. Get your audio interfaces for Lab 5 if you haven't. Okay, these are these things. Okay, these things for Lab 5. Okay. I'm monitoring simplex cal during the day most of the time if I don't have meetings. KB6 LED. Feel free if you have questions about the project. Try me. Maybe I'll pick up. So somebody at midnight last night called. I answered. So give it a shot. Eventually, maybe. So thank you for everybody participating in the net. That was fun. At some point, when you have the interface working, we'll do maybe a digital net. Okay, so I think that'll be even funner. Okay, so what I want to do today is talk about Lab 5, Part 1, and then that is now has been polished, I think, to a level which unprecedented compared to last year's. That means that I don't know what it means really. It means that there's more debugging information for you, so hopefully you'll be able to solve things relatively quickly. Okay, it will be due next week. Okay, so this is not like a 2-week thing for these labs. Now we're running a little bit on a faster schedule. It's going to be due next week. Next week's checkoffs for that one. We want to make sure that these interfaces work for you, and because without that, you can't do anything. Okay. All right. So the purpose of this lab is to make sure that everything works with your radios and the interface. This is really the purpose. And also give you tools to work with it. We wrote some tools to use buffered audio. We wrote tools to control the PTT through USB to serial. And we want to go through some experiments here so you know how to use these tools in certain modes of operation that you can use for the later part of Lab 5 and also for your project. But one of the things that I want you to get out of it is kind of also thinking about how to debug things. Because you're going to dealing with real signal measurements with different interfaces. So there's the computer, there's the audio interface, there's the radio, there's the SDR. All of these needs to work at their right level. And so this is we're going to show you some examples of how would you go about and debugging some of those that maybe it's hard to measure. So how do you measure those? Okay, so you're getting this audio interface, and the audio interface has a USB hub that connects to your computer. Then you've got the USB audio. This is basically your DAC, digital to analog conversion, and your analog to digital converter. Okay, it's a $2 one. Okay, I'm just shocked like how inexpensive things have become. It's not an amazing one, but it's pretty good. Okay, it is pretty good. It works at 44.1 kilohertz. Okay, so what else do we have? So this DAC is connected through a ground loop isolator, which is basically a transformer, an audio transformer, just to make sure that there's no DC bias that goes to the USB hub. It goes through a cable. There's a choke here. The choke, the idea is that this cable becomes an antenna, and so we want to minimize interference. So current flowing on the shield of this cable can interfere with the audio interface, can interfere with the USB, with this device, can interfere with the USB hub. It will interfere, even with that choke. So you have to kind of work, where to put it. Don't put it on top of it. Don't put the antenna aligned with the cable. The worst thing you could do and transmit, okay? Don't do that, okay? I've seen this. I've seen stuff like that. People put this, and then it doesn't work. The lab doesn't work. It's like, right, because your computer starts to light, like your LEDs on the computer are just now lighting because you're transmitting, and all this energy goes. So just think first of all. You have this. Put it here. Make sure there's a choke, and then connect this, and then try to make not too many cabling lying around, and low power and things like that. So you have to work with this. This is part of the thing. Okay. So this goes in and allows you to put audio into the radio and pull audio out of the radio. It also allows you to control the PTT, and the way that it's implemented is that when you connect the two grounds of the input and output, the radio keys. Okay, so we do that by shortening using this USB to TTL. Okay, so this is a a USB to serial device, it basically puts a voltage or no voltage, 3.3 volts. Okay, and so you can control this. All these cabling are not the greatest thing in terms of system design. They could create a lot of interference. Ideally, everything should be small and isolated. But we also wanted you to see that you can actually build that kind of thing. So it was kind of a compromise between making something that would be more dedicated to something that you can, I can do that, right? You can do that. Okay. In hindsight, I don't know what's but this is a nice one. It works really well. It works really well, but you have to work with it. Okay, so we can control this USB to TTL to key the radio on and to key the radio off. Okay, so there's a lot of information on the lab. Please read all the words very carefully because we put all this instruction and comments and suggestions. Please read them because going through them will really minimize any pain that you might have. Okay, so there's instruction how to install things, how to use, how to operate, how to debug. So read them carefully. Okay, we provide functions for buffered audio using threads and queues. Python and threads, the threading library is not great because you can't kill it. Okay, the multiprocessing is much better. We can get it to work with PyAudio. So we'll try to do that before the next parts, but we're having trouble with it. So we decided to stay with this. So threads are tricky. But what we did is we added these queues to control the thread. So you can communicate with the thread and then tell it to kill itself. Basically that part we added. And so now it works quite well. I was able to not have to restart the kernel 100 times, right? Maybe 2. Okay, so it's reasonable. Okay, so one thing that you need to do is, first of all, to find what is the USB audio device. If you're going to use Windows system and if you're going to use Mac system or Linux system, they're going to be slightly different. Okay? If you're using Linux, I trust that you're computer savvy and you can figure that out. Okay? If you use Linux, then you're savvy. So you can do it. If you're using Macs or Windows, then we provided this function for you to look at the basically, it spits out the numbers for the audio interface, and you need to figure out which one it is. So for my computer, the second device is the USB audio. This is the built-in output. This is the microphone. Now, what could happen is that you log into a network. There's an Apple TV. You take which is an audio device that suddenly appears. And then you disconnect the USB, you connect it back, it changes the numbering. Okay, so if you're suddenly nothing works, you don't get audio, it might have been that your numbering have changed. Okay, we used to have actually an auto detection function that would look for this USB PNP device, but it wasn't as robust. So we think this is a better solution. You can write your own function that looks for this particular device. Once you know, because there's different variations of this chip, they have different names. And they appear differently on different computers, different Windows versions even. Okay, so you have to figure that out. The next thing is we want to make sure that the audio that comes from the radio into the audio interface is not clipped, is good quality. How do you do that? Well, you do that by basically measuring. Okay? So you have to set the input audio to your computer with there's a microphone input level for the USB device that you need to set. Set it to half. Okay, so it's not too strong and it's not too low. Something like this. And then you need to set the dial here of the audio output level too. Okay? Set it to a quarter or something like this. Or maybe half a turn. Okay, so and that's where you should start. Then you're going to record from the radio, either by having somebody transmit to you or use the radio function, because you can listen to radio using this, and then record some audio. And then we have a function that basically computes the peak signal on a buffer of 10,024 samples and the normalized RMS, which means square power. And then you could see how it changes over time. And then you want to make sure that this is not clipped, and it's about 0.4, 0.5, but not above 0.6. Okay, so the peak should be above 0.6. Then that means that your ADD would be in a good range, and it would not be clipped. Remember when we talk about quantization noise. Okay, so this is one way to debug the input. Okay. The next step is to be able to transmit. You want to make sure that you can transmit. So we have this. We use pi serial in order to control this serial port, and then to key the radio. You need to find, again, what is this device. On Windows, it will be some COM something. And there's instruction how to look for. On Macs, it will be /dev/tty.slab USB to UART. Okay, and it could have some like 1, 2, 3, 4, depending on various things. So you need to go and figure out where it is. Then this is the point where probably half of you will have something going on. Because this code, in this example, sets DTR, which means that it's going to transmit, and then key off. Key on, key off, key on, key off, key on, key off. Okay. By the way, when you set the pi serial, when you actually import pi serial, it starts transmitting. So you immediately need to stop it. Okay. So if your radio starts transmitting, first of all, the first thing you should do is disconnect this, because then otherwise you can't really stop it from transmitting. Okay. I don't have to say that before doing any experiment, you should set on your experimental frequencies low power and identify yourself. Make sure also that nobody else is using those frequencies. So there's 10 of them. There's 40 of you. So, manage them well. Okay. There's some more channels here that you can work with them. Okay. So make sure that you're working on a channel that people are not using. And you can see it if the green light turns on and off all the time. It means that there's something going on. Okay, now the reason it's point of failure, because when it starts to transmit, then if there's coupling into the USB, then maybe it's going to stop working, if this is not working well. Now, if you cannot sort that out, maybe you have some RF interference, maybe we need to give you more chokes, so we can give you more chokes, and you can put them on the cable. There's chokes already, but you can put more. And that often solves the problem. By the way, putting another, a coil of the cable on, that actually helps increase the inductance. Okay. We also implemented, so beyond just controlling on and off, we implemented the ability to key the radio through the data channel. So when you send data through the queue in order to transmit it, you can also send commands. And the idea there is that if you want to synchronize the keying and the data that you transmit, you want the same function to do that. So you can input in the queue that you send to the data in order to play the audio. You can input key on and then put the signal you want to transmit. So that will turn on the transmitter. There is actually a default wait time where you can control it. That lets the transmitter ramp up. I think it's 200 milliseconds, but you can modify that to make it shorter or longer if you want to. And then we'll play that. Then you can do key off. Then you can play another signal. You can key on. You can put waits by basically not doing anything, like put zeros without keying anything. So all this stuff you can play just by putting things into the line. And then if you want to quit the thread, you send end of thread. Okay, so this is a way to control. This is one way that we figure out that will be a useful way to control the radio. Okay. All right. Any questions? It's going to be fun, I think, to play with. I mean, I have to say, this is. And if you do it in pairs, then it's nice if one person transmits, the other one also receives with their radio, so you can get feedback on how does it sound. Also, because sometimes if there's interference, it might not kill this device, but it might create some tones, and you'll be able to hear them. So if you move this, you see, oh well, it doesn't have that anymore. Okay. Okay, calibrating the audio. So the other thing now, we want to calibrate the audio level from the computer to the radio. This is harder because we don't know what the radio is hearing. Okay, so that's a little bit harder. For this, you need another radio or another way to do this. I mean, we could measure, the voltage, like with a scope, and like know the specs of the radio, but let's do it the hard way. But not the hard way, but like a measurement way. And the measurement that we don't trust, for example, the specs of the radio. And so the way we're going to do it is we're going to play from the computer, transmit with the radio, and receive with a software-defined radio, with the SDR. And we provided you, for those who have limited access to USB, there's another now cable for this that can also serve as an antenna. So be careful. Okay. So when you don't use the SDR, well, I don't know, disconnecting it can break this, so be careful. Okay. So the SDR. The one thing you need to do is take the antenna out. Why? Why not connect the antenna of the SDR? Think. What do you think? Come on, wake up. It's next to the radio. A lot of power is being transmitted. Okay, if you have an antenna, it's going to be really coupled to it, right? The SDRs are tuned to listen to really far away signals, right? Like microvolts. If you've got a 5-watt or a 2-watt transmitter, because you're going to do it low power, next to the SDR with an antenna, I mean, it's going to overdrive it no matter what. Actually, if I have the SDR here with an antenna, I'm going to transmit from here, it's going to overdrive it. So it's just too much. And so you want to take the antenna off to minimize, and don't worry, the signal is going to be huge. Okay? So that's like one example. Okay? Don't put it close. Okay? Put it far away, because it will be enough. The other thing is you need to set also the gain of the SDR to be low. Again, you don't want to overdrive it too. Okay? Now, how do you make sure that the input from the audio to the radio doesn't saturate? We want to find the point where things are behaving still linear. Okay? So what we're going to do is we're going to drive a tone with increasing amplitude from 0 all the way to 1. Okay? Digital amplitude. And then we're going to see what is the response. And here's the spectrogram of the response. So first of all, when the radio keys, then there's it's just the carrier. And then here, after about half a second, we start playing the audio. And as you can see, the bandwidth increases. This is FM. Why the bandwidth increases when you increase the volume of the audio? Right, because in FM, amplitude translates to frequency deviation. Right? So if this was linear, then it would have been increasing. Right? But it's not. It's saturated at some point because, first of all, the radio has a filter in the output that doesn't let you transmit beyond 12 kilohertz bandwidth. Okay, so that's going to clip it. And also, maybe there's some other clipping that can happen, in the middle. So we want to figure out where things are linear. Okay, so you're going to receive the signal. You want to make sure that also your SDR is going to have an offset. You need to find the offset and correct for it using the PPM. So it might require maybe a couple of iterations to do that. Okay, so this is a perfect one, but that's not the case. Probably you're going to see this a little bit with an offset. Okay, so you have to correct for it. The radio also may have an offset, so they need to correct both from this. You need to make sure that they're listening to the same frequency, or thinking they're listening to the same frequency. Okay, so then you need to FM demodulate it by low passing, decimation, limiting, and discriminating. Okay, and then this is the result of the spectrogram that comes out. This is a pure tone. In this case, it was 2.4 kilohertz. I'm not sure exactly. We'll put. I think that your tone is going to be somewhere around that. And then you're going to look. What you're going to do is you're going to do a bandpass filter, a complex single-sided complex bandpass filter about that frequency, which will give you the envelope. And then you're going to display the envelope, and you're going to see it increases linearly, and then at this point it starts tapering off. Now that point is going to depend on what is the audio level that this thing outputs. If you set the audio level to be high, this thing happens quickly. If it's low, then things happen a little bit more slow. But they will saturate. Or if it doesn't saturate, it means that maybe your audio output is a little bit too low. Okay? So you need to find what that point's for your setting. Once you know the point for your setting, you know exactly what is the amplitude they need to scale all the audio in order to make sure that things are linear. Okay? That's cool. Right. I was pretty excited about that. I don't know about you. First of all, I found that I was completely oversaturating everything. I didn't realize that was the case, but it's not easy. It's not hard to actually saturate. Now, as you increase, you get a little bit more gain, but this part is nonlinear. So when you do digital, you probably don't want to operate in this nonlinear regime. Okay? So I hope that will actually solve a lot of issues. So you want to figure out what is the linear regime, what's the nonlinear regime, figure out what that amplitude is, and then use that amplitude. Okay. Now the last thing before the last thing you're going to do is measure the input frequency response of the radio. Right? We're inputting certain frequencies, but the radio has a bandpass filter. First of all, it throws away low frequencies, throws away high frequencies, but it also pre-emphasizes the high frequencies too, like 2 high frequencies. So within a band, it actually has a 6 dB per decade ramp. And the idea there is because when you do FM modulation, the high frequencies actually are more noisy. So what you do is pre-emphasize the high frequencies so that the noise is uniform. Okay? And then the radio on the receive side, these radios put it back down, okay, by correcting for it. But the SDR doesn't know that. So the SDR will able to measure the input filter. Okay? So the SDR doesn't do the filtering, but if you transfer from radio to radio, this emphasizes, the radio that receives de-emphasizes. Okay? So you're going to see it emphasize. So what you're going to do is 2 methods. One of them is to transmit a chirp, that you're going to sweep frequencies, and then demodulate and look at the response. And the other one is you're going to generate noise. You play noise. Noise, wide Gaussian noise. Wide Gaussian noise has uniform amplitude in all frequencies. And so if you look then at the power spectrum of the noise after receiving it, you're going to see that it's going to be colored. And the coloring means that you're going to see the frequency response of the filter too. That's another approach. So one way to calibrate things, usually people use calibrated noise sources to put that through the system and to be able to measure outputs. And so this is kind of what we're going to do here. Okay. So here's the response for a chirp. Here's the response for noise. Okay. You see that it's being weighted. You see that this is weighted over time because this is a chirp. Okay. So you see the difference between these two. And then this is the frequency response for the chirp. You see these spikes. Again, these tones are due to RF interference that created some tones in the audio. You don't see it here because we have to do averaging, and so it's just of different parts, so it doesn't become coherent. And so you can see pretty nicely how there is a ramp up to 3 kilohertz, and then it goes down. Okay. So that's pretty cool. It also tells you that it will affect your ability to do good. Like if you want to increase the rate, for example, of your modem later, you kind of know now what frequencies it can actually operate with. One thing that we didn't do is measure the input filter. And if you want to do that, you can basically run a de-emphasizing signal. So if you transmit a signal that is actually weighted the opposite way, your radio will then whiten it, then transmit it. You receive with another radio, record the audio, and then you'll be able to record the input response of the radio. We didn't do that because you need 2 radios for this. Yeah.
On the bottom plot on the left, it's like a slope downward. What is that?
This?
No, on the left all the way.
Oh, this part?
Yeah.
That's, I think, the noise just in the system.
Okay.
So there's some low frequency noise, right? So maybe some DC bias too that went through. There might be some DC bias too here. Yeah. Again, this is noise power spectrum. Right? So if you have some. So what you could do then is like compensate, send it, get a white response over the air, and then when you get back, then you could come up with what is the input filter. Okay, but you need 2 radios to do that. That would be useful if you want to improve your detection for the for the project. So the last thing you're going to do is you're going to have a function that generates Morse code that you can transmit your call sign automatically. And the thing about that is that now, in the future, all you need to do is before you do experiments, you just call this function. It sends your call sign, identifies you, and then you can do your experiments and then end up with identification. It's enough to identify yourself with Morse code. Okay, so then just to make sure that you're within the requirements for the FCC. Okay. So this is part 1. Not all the things you need to implement yourself. There's part of the things you implement yourself. Some parts will just give it to you, and you have to go through. And please look at them very carefully. Okay. The next part of the lab would be AFSK modulation and APRS, like ND modulation, and then APRS, where you learn about how you would take a physical layer and add a packet layer that you can transfer the information on top of it, and then you'll be able to send APRS packets, send SMS messages to friends, emails to friends, and text message among yourself. Okay, so that's the other parts, but this needs to work well. Everybody should check off next week, okay, by Thursday. I'm excited. I'm going to have my radio on an experimental channel just to hear that. Okay. Let's talk about multidimensional signals. So something completely different. So as it turns out, a world is not one-dimensional. And we kind of touched this before, right? Like you realize this, right? It's not one-dimensional. Even though some people have a certain trajectory in their life that they just go, school, go to university, grad school, then go to, work at a company, and then die, right? But the world is not one-dimensional. You can actually look to the sides, look up, look down, and do lots of things. One thing that is not one-dimensional, that is completely saturating, well, this is not saturating the net, but used to take a significant portion of it, but definitely takes a significant portion of our phones, our images, which are 2-dimensional. Videos are 3-dimensional signals. And those take a significant amount of information now over the internet. Like this is the number one resources. I think Netflix is like half the internet, probably, or something like this, in the U.S. at least. And then, like if you take YouTube traffic, Facebook video, all this video stuff, this takes just most of the traffic in the internet today. But you can also see that in the future you'll have, for example, dynamic 3D scenes, so virtual reality. Well, you have 3-dimension in time, so it's 4-dimension, and you can even think of medical images, which actually even have higher dimension, or computer graphics, that if you think of a scene, actually has way more dimension if you look at the light fields, the reflections from different places, different parts of the scene, and so on and so forth, then it becomes much more significant. So we're not going to look at the analysis of this multidimensional signals. We're going to mostly focus on 2D. And I want to show you one of the application of 2D, which is very different than 1D, is the application for tomography, even if tomography can be done in 3D and 4D too. But then next time. So before we go to discrete, let's talk a little bit about continuous. I know, have anybody here have taken an image processing class before? I think it's 225B, 145. Which one is the image processing? Okay. Yeah. So some of the functions that often you see is, there's a delta function in 1 dimension. There's also a delta function in 2 dimension. Delta function in 2 dimension is an impulse at x equals 0 and y equals 0 and 0 elsewhere, and it has a unit area. Okay? But you can also write a delta x, which means that it doesn't have any variation in the y dimension. It's a 2-dimensional function. And this would be an impulse line. Okay, so it's a line that has an impulse along the entire y-axis, okay, and at x equals 0. And in that case, as it turns out, if you integrate over the entire space, it doesn't have an area 1. Actually, its area is infinite. Okay. This is another function that we've seen before, so a rect function, so the boxcar function. But you can also write it in 2 dimensions. So in 2 dimensions, it will be basically like a box, something like this, that sticks out in 2 dimensions. Okay. You can also define spatial harmonics, so cosine with a function that changes in x, but also in y, and that basically depends on where this function is going to be. And then you can also have, because it's 2 dimension, you can have circularly symmetric, for example, functions like the boxcar. This is a. So a boxcar of R, so it only varies with the radius. Then in that situation, you'll get basically kind of like a circle that sticks out of the plane. Okay, so it's like a pillbox. So if you talk about signals, you can of course talk about spatial frequencies in a similar way. So if you look at, and we call it spatial frequency because often we think of images as have spatial coordinates. So instead of using time before, we're using space, like centimeters, meters. But it doesn't have to be. It could be a combination. You've seen before, spectrograms have 1 time and 1 frequency. These are also 2-dimensional signals. Okay? Or 2-dimensional analysis of maybe a 1-dimensional signal. But you can also define a spatial frequency. And a spatial frequency can be defined in the following way, where you have a angular frequency in x and an angular frequency in y, or you can write it in this particular way, where these are actually in 1 over centimeters, or 1 over meters, or 1 over millimeters. So it's 1 over distance. So if x and y is centimeter, fx is 1 over centimeter, and omega x, omega y is radians over centimeters. Okay, so the units are now changing. But again, it's same, but and different. Same, different. Okay, here's an example of a spatial frequency. Spatial frequency, here's a case where you embed a temporal frequency that's 1-dimensional in a 2-dimensional space. So vinyl records are back, right? Actually, have the sales of vinyl records over the last couple of years have increased dramatically. I don't know why. It's not good quality. But I have to say, there is this goodness. It's pretty nostalgic. I remember when I grew up, I had a vinyl record, and this is how I used to buy stuff before CDs came out. So I still have some kids' vinyl records. We went back my parents' home, and I played to them some vinyl records. I was like, "What is this plastic?" And we put it, it's like, "Oh, it's rotating. Oh, it makes sounds. Oh, that's pretty cool." And then it makes all this click click because of the dust, and then of course it skips lines. But I think it's pretty amazing quality for the analog type technology that it is. So you have these grooves that basically, when you have a needle going through, it vibrates at the particular rate, a certain rate, and that is of course adjusted to where you are in the radius, right? So here you actually have to change faster than you have to here in order to represent the same temporal frequency. But it's really just embedding a one-dimensional signal into a two-dimensional space. CD-ROM are similar things, except they're digital. Okay, you have ones and zeros that represent. But we'd like to look at real, pure two-dimensional signals, not just 1D embedded in two-dimensional space. And here's an example of some sine 2 pi fx plus fy. Any idea which frequency is this? And how do you even figure that out? B? How do you know? Negative 1 to 1 in x direction, and? Okay, so you count. 1, 2 cycles per 2 centimeters. This means 1 cycle per 1 over centimeter. Okay, and then here it's constant, so 0. Hence, fx equals 1, fy equals 0. Okay. And what's this one? What do you think? C? Okay, C. First of all, is this a cosine or a sine? A sine? Cosine. That's right, because it starts at a positive as opposed to being at 0. Okay? That's right. And then let's see, fx equals 0, no changes, and then 1, 2, 3, 4 cycles per 2 centimeters, so fy equals 2. Good job. And what is this one? A would be, okay, so 2 cycles per 2 centimeters, so it's fx equal 1, and then 1, 2, 3, 4 cycles per 2 centimeters, so fy equals. So that's great. So the fact that I have now f and x and fy is just basically rotating my grid. Okay, so this is still a linear frequency across space. And then here's an example of a vinyl record. What will be, if the vinyl rotated at 1 hertz, what will be the frequency? What? Yeah. Is the frequency increasing? On the vinyl record, it does increase. But here it doesn't, because the angular frequency is the same. Right? Because if you actually look here, the spatial, like the the spatial frequency actually increases in the same way that the temporal frequency increases. So they increase in the same way, as opposed to a vinyl record, which is not the same way. So you've got 8 cycles, 8 cycles, and 1 hertz, so it'd be A. Yeah. And what about this one? So what's the answer? There's 100 of them. Who says, okay, so this doesn't make sense, this doesn't make sense, right? Because we're not idiots. Okay. It's this or this one. Could be a pop quiz question. Come on. What do you think? 0 or 1 is a binary decision. What do you think is more likely? Soft decoding. You want to pick one? You have to commit. D. Good choice. Why? Like, that's where luck plays a lot. Okay. So yes, if in the beginning it would actually play 100 at 100 hertz, but when it gets to the center, it starts aliasing. Okay, so when it gets to the center, it would not. Right at this point, it would actually not play anymore. And the reason is because there's not enough spatial resolution that I can actually represent this. And this is why vinyl records have a sticker. Because you can't really encode high audio quality at that because you need really fine spatial resolution. It was not possible. It would cost a lot of money too. So this is one of the reasons. And also there's not a lot of time then there. Right? There's not much space, so they just give it up, put a label. Okay, so once you have spatial frequency, you can also define then the Fourier transform. And the Fourier transform of a two-dimensional Fourier transform is, again, what's surprising is just instead of using one integral, you just do 2. Okay, you integral over 2, and then you have an fx and fy over x and y. Okay, so it's pretty simple. And it's simple in the sense that, let me show you. If I take, for example, a brain image, I compute the Fourier transform. This is the magnitude of the Fourier transform, where this is fx and fy equals 0. This is positive x, this is positive y, negative x, negative y. Okay, so it's two-dimensional Fourier transform, and it has variation in amplitude. I think this is also the log of the absolute value. Otherwise, you'll be able to, basically, you just see like this bright thing, and that's it. You know. And the reason you get a bright thing for an image, because an image has a strong DC component. It doesn't have a negative component. So it has to have a strong DC component. Okay, an image has an intensity, it doesn't have a negative. Well, it could have a negative, but that's not what we measure, for example, from cameras. In MRIs, it turns out you can actually get a negative. So as I sweep through the spatial frequency and then I try to take an inverse Fourier transform, you see that the high frequencies really represent edges. Okay, edge information. So here you see as I build up, you're going to see like an edge map. Here, see edges? Edges in this direction, and as I cross the center of the frequency domain, then you get the low frequencies. Then you can say, okay, here's some examples. If I have a sinusoid going in this direction, the Fourier transform would be 2 delta functions. If you can also display that as a surface, and then look at those impulses. And then if it's higher frequency, then what would happen to these delta functions? Right? So the closer these are, then the further these are. Okay? You can also then say, okay, what's a two-dimensional sink? I have a sink in 1D and then multiplied by a sink in another dimension. This is this function, sink in 1D, sink in another dimension. Oh, Where do you go? Okay. Going. You see this bug? So the sink in one dimension, sink in another dimension. You see that the sink is spread more in this dimension, and it's more narrow in this dimension. In the frequency domain, is the opposite. Right. So if you compute the frequency, then this would be more spread because more bandwidth, and this would be more narrow. And here's another example where you've got a really, really kind of wide sink, really spread out, and then here will correspond to a really small box. Okay, so this is great, but we want to do things discrete. So in the discrete domain, we can then define a DTFT in the same way that we define a DTFT for one-dimensional. And in that case, I've got omega x and omega y, and it will be the sum over minus infinity to infinity over the indexes with omega x, and it will be periodic with 2 pi. But it will be periodic in 2 dimensions. For this type of a grid at least. And then another representation is where you use actually kx instead of omega x, which means the only difference is that kx, instead of being from minus pi to pi, they just go from minus 0.5 to 5. So these will be like digital frequencies, not digital angular frequencies. I like this better because the inverse of that doesn't have 1 over 2 pi. This is symmetric inverse in 4. So I prefer that one. So you could actually show that if you actually massage this equation, you can see that basically performing a DTFT in one dimension, then followed by a DTFT in the other dimension, is the same thing as computing those two sums. So you can separate the computation into one DFT followed by another DFT, which is cool. Last thing I want to talk before we finish for today and I'll release you is you can also define a DFT, and the DFT is basically sampling of the DTFT. Okay, so exactly the same thing where you have a forward and inverse. And again, I told you that I like a normalized DFT, which is 1 over square root of NM, because then it's again symmetric. And what you need to remember, though, when you compute this is that the index of 0, 0, it's at the edge of the image. And 0, 0 in frequency is at the edge. And if you want to represent, again, the DT, like a representation where the middle of the image is x equals 0, and also the middle of the image is fx, then you need to do FFT shift. And FFT shift in 2 dimensions still works. You have all the properties of circular convolution. They all apply in 2-dimensional. Circular shift will be then a modulation in a very, very similar way. You want to give me a couple minutes to show you just an image? Because it's like you can't really finish an image, a lecture in 2D without showing an image, right? Okay, so here's an MRI phantom. This is a phantom made of plastic with water in it. All the bright stuff are water. And we used to calibrate scanners using this. And it has very particular shapes here. Of course, the G logo, this is a G scanner. And then this is the magnitude Fourier transform. And you see that there's a few interesting features in the magnitude Fourier transform. Let me point out one, which is these. Any idea where these are coming from? Have you seen this before? Maybe 20. Did you take 20? No. Liar. Right, so the comb here, what is the comb? Comb is kind of like a delta train that is then cropped by erect. Right? It's a delta train multiplied by erect in that direction. So if this is periodic, and then it should be periodic too. And it's also convolved, by the way, with... so it's a delta train convolved by a small rect and then multiplied by a big rect. Okay? So convolved by a small rect means that you are going to be multiplying the frequency domain by a large sink. Okay? And then multiplying by rect means that you'll be convolving by this. So these are a little bit spread out. They're not like point because it is cropped. And the reason that this is weaker than this one is this sink that's weighting it.